Okay, camera died, but I'll go through what I was saying. So we have kinetic energy here. The amount of kinetic energy is 1/2 mv squared. Here it's stopped, so the energy would be here, or 0. So then the change in energy, right, from 1/2 mv dot squared to 0 is just going to be a change here. I'll write it up here. Change in energy equals Ft. The change in energy would be minus 1/2 mv naught squared. It's the friction force that's doing the work, so I'm going to replace this with force of friction. Force of friction is mu Fn. Mu is given. The normal force, right, on a level surface, the normal force would just be mg, so I'm going to replace F with mu mg, and then distance is what I'm looking for. So you'll notice the m's cancel out. Yes, I have a negative here, but technically my friction force would be negative, so that's going to cancel out. And now to get d by itself, divide the mu and the g over. So I've got 1/2 v naught squared over mu of g. Now none of your answers actually look exactly like this, but I can rewrite the 1/2. Multiplying by 1/2 is the same as just dividing by 2. So then that's going to be just 0.8. Ignore this. Pretend you don't see this. So we're looking for this system. It's going to be released. This one is obviously going to go up. This one goes down, and it says when it has moved 4 meters. So first let's find the change in potential energy. Each one is changing. This one's going up. To find the amount of potential, you just do mgh, so 0.5 times g times the height that is changed, gives me a change of 20. This one, mgh, but now I have a different mass, so that's giving me a change of 30 joules. Now, this one went up, which means my potential energy increased, so I gained 20 joules. This one went down, which means our gravitational potential energy decreased for this mass, so that meant I lost 30 joules. Now, if I gained 20 joules and I lost 30 joules of potential, then overall you lost 10 joules of potential energy. So that means we're between B and D. Now, if you think about your kinetic energy, right, so at first it was at rest and now it's moving, so the fact that it went from 0 to having some kinetic energy means my change in kinetic must have been positive because you're gaining kinetic because it started with 0. So that means your answer is D. The other way to think about this being positive is we know that energy is conserved here because we're talking about frictionless, so no work is being done, energy is conserved, so any potential that I lose has to go into kinetic energy. And it has to be the same amount. If I lose 10, that means I gain 10 here. 7, we've got a 10 kilogram box released from rest at point A. So because it's released from rest and it has a height, that's only potential energy. When it reaches point C, it has a speed of 6. So obviously it has kinetics, that has a speed. It also has some height, so it has some potential. I want to find the work done by friction. So 2 ways to find work. One is FD, the other is change in energy. You don't have these like distances and you wouldn't know like the forces, so we're just going to use change in energy. So find the energy at A, that's going to be mgh. mgh gives me 500. This one is m of 10, gh of 2, and 1/2 m velocity of 6 squared. So in total that gives you, I don't know, 380? Yeah, so this one you get 380 joules. So if I start with 500 joules and I end with only 380, obviously energy was not conserved, work was done. So do final minus initial, that has a work done of 120, negative 120. And make sure that you have a negative work done because your energy is decreasing. Also at every single point, your friction force would be opposite to the displacement. 300 meter high skyscraper, I've got a 2 kilogram ball that's thrown downwards with an initial velocity of 20. When it reaches the ground, it only has a speed of 60. How much energy was lost to friction? So think about here, you've got both potential and kinetic. When it hits the ground, right, it's coming down with just kinetic energy. So let's go ahead and calculate how much. 2 mg plus 1/2 m velocity of 20 squared. Here it's just 1/2 m of 2 velocity of 60 squared. So I've got 360 here, and I've got 6,400 here. That's not 360, but that's okay. If I start with this many joules of energy and I end with this much, how much energy have I lost? You just subtract, and that is losing to 2,800. 2 frictionless water slides shown in the figure. Both drop over the same height. One is straight, one is curved. What is true about the velocity of this guy when it comes down compared to this guy when it comes down? So let's think about. Here it says frictionless, which means that energy is going to be conserved. They both start with a height h, so that's mgh. They both end with just velocity right here, or just kinetic energy, which is at 1/2 mv squared. Now, no matter what their mass is, we're going to be setting them equal. So see how the m cancels out? So the only thing this velocity depends on is how high it started. They both start with the same height, and it's frictionless, so energy is conserved, so they both will have the same velocity at the very end. Now, which one hits the water first? So energy has to be conserved, but energy doesn't have anything to do with the time that it takes. So here, right, we look at this one that is gaining speed steadily. See how this one is steep at first? It gains its speed, and then it cruises at that fast speed for the rest of it. So the one that hits the water first would be slide 2 because it is a faster speed on average. It reaches its fast speed before the other one. Alright, we've got a toy car. It's got a height h and a velocity of v naught right here. Assuming there's no friction, no work done, so that means energy conserved. What is the speed at point y? So here you've got both potential and kinetic. Down here you should have just kinetic. So potential would be mgh plus 1/2 mv naught squared equals just kinetic 1/2 mv squared. I'm looking for this velocity. Your m's are going to cancel. Multiply by 2 to get rid of the half, so that becomes 2gh plus just v naught squared now. And to get v by itself, you take the square root. So then your answer is C. We've got a block of mass 0.05. It slides at a constant velocity. So this is, well, it says velocity. I don't know where I started to label that. And then it comes to rest when the spring is compressed. This is your spring constant. It compresses 20 centimeters. So that means your x is 20 centimeters. We don't like centimeters. We like meters. So divide by 100. You get 0.2 for your x. We want to know what is the change in the block, earth, whatever system energy. So think about it right here. I have all kinetic energy. And then when it comes to rest, as the spring is compressed, that's going to be all spring potential energy. I'm not going to set them equal because it's asking me how it changed. So let's not set them equal. Let's actually just find it. This is going to be 1/2 m. V naught is 10 squared. So this gives me 2.5 joules. Here, this is spring energy, which is 1/2 kx squared. 1/2 k is 100. X is 0.2 squared. Multiplied gives me 0.2, not 0.2, just 2 joules. Alright, so I had 2.5 joules, and now I only have 2 joules. So then how much it decreased by was decreasing by 0.5. A ball falls from the top of the building. Through the air friction is present, so not conserved, energy not conserved here, work being done. How does the kinetic energy just before striking the ground compare to the potential at the top? So think about, I have some potential energy right here. It's going to come down, and I'm going to have kinetic here. Now, normally these two would be equal, right? If energy was conserved, all the potential would go into all kinetic here. But air friction is present, so energy is not conserved, so we can cross off A. Now what we know is that I'm losing some of my energy, so then K must be less than your potential energy. So K is less than U because some of that energy was like negative work losing into friction. A block of mass M5 is moving up at 10 meters per second at point A, so 10. So I have kinetic energy here. The block is not frictionless, so it comes to a stop. So at this point it comes to a stop, which means I have only potential energy. They are not equal because it said it was not frictionless. I want to find the actual force of friction, so I'm going to use work, which tells me that the change in energy is equal to Fd. I'm looking for the force. The distance traveled would be the 4. And now I just need to find the change in energy. So how much kinetic do you have? 1/2 mass of 5 10 squared gives me 250. Here, this would just be mass of 5, not 10, times g times height of 2, which gives me 100 joules. So from 200 to 100, I obviously just lost 150, so my change in energy is negative 150. Divide the 4 over, that gives me a force of this. And technically it would be a negative force. Person lifts a box from ground to table, so it starts here and then it's lifted up to this height. So it started here, went to here. It was at a constant speed, which means that KE is the same. Now my potential energy obviously is not the same, right? I went from the ground to the 0.6. That means that my potential energy increased. So if my kinetic stayed the same, but my potential increased, that means overall my total mechanical energy must have increased. So we're between B and D. Now the only reason your energy increases is if you do positive work. Also, as you lift it, right, your force is up and the displacement is up, so that would be positive work as well. Alright, we have two blocks. They're sliding down from rest. They're the same height, and they have the same coefficient of friction. So energy not conserved. Energy not conserved. How did each ramp's change in potential compared to each ramp's change in kinetic? So let's think about their change in potential. This one starts with MGH and goes to 0 potential energy. This one starts with MGH and goes to 0 potential energy. So they should definitely have the same change in potential, right? They started and ended with the same potential. Now, kinetic, this one started with 0 kinetic, this one started 0 kinetic. Their kinetic energies are not going to be the same because energy was not conserved here. If you look, right, they have different force of friction and different distances. Ramp 2 has a greater force of friction and a greater distance. Ramp 2 has more work done. That means it's losing more energy, so it'll have less K than this guy's K. So ramp 1 has a bigger change in kinetic because most of its potential is going into kinetic, whereas this one is losing more, so it has less change in kinetic. So ramp 1 has a greater change in kinetic because most of its energy goes here, whereas this one loses a lot of its energy, so it has less going from potential to kinetic. Which one reaches the bottom first? Ramp 1 for a couple different reasons. It has a faster speed because it doesn't lose as much, and also because even if it was frictionless, this would reach the bottom first because it has a greater acceleration and faster average speed because it's steeper. On top of a 300-meter skyscraper, a ball is, this is a typo, it's supposed to just be dropped, can't be thrown and dropped. If 100 joules of energy is dissipated, what will the velocity that it reaches the ground be? So think about, if I drop it, I have just potential energy. Potential here would be, I think, 6,000. Yeah. Now, if only 100 joules is dissipated, then the kinetic energy it reaches the ground with would be 5,900. And then if that's my kinetic energy to find the velocity, well, kinetic energy equals 1/2 mass of 2v squared. So the square root of 5,900 is your velocity, which is like 76 point something. Alright, object starts in rest and a force is applied. The force applied is shown as a function of the displacement. As soon as you see force distance graph, you should find the area. So the area here, base of 0.1, height of 20 divided by 2 is an area of 1, and the area is going to represent your work. Now, I need to relate it to what's been given. It says it started from rest and acquires a speed, so I know V naught is 0 and the final velocity is 2.4, and I'm looking for the mass. So obviously, when we're using that work is equal to change in energy, it's the kinetic energy that's changing. So I'm going to say that work equals change in energy, in this case change in kinetic. So work equals 1/2 mass 2.4 squared minus 1/2 m0 squared, which goes away. And then you're just rearranging this. So this is just 2.88 m. Divide over, that gives me a mass of 0.35. Alright, a box of mass m is released from rest on a rough ramp. So friction, right? Energy not conserved. The box has a velocity of v at the end, and I want to know what is the force of friction. So think about, we just said that energy is not conserved, there is work done, so I'm going to use that change in energy is equal to Fd. The change in energy is not just potential, but it's not just kinetic either, right? I'm starting with mgh, and I'm ending with 1/2 mv squared. If these two are not equal, then the change would just be this one minus this one. So the change in energy would be 1/2 mv squared minus mgh. And that's going to be equal to the force of friction, which is what I'm looking for, times the distance traveled, which it said the distance traveled is just the length of the thing, which is L. So then you just divide by L, and that's your answer. 1 kilogram block is attached to an uncompressed vertical spring of spring constant, so that's my K. They hold the position, oh, that's my mass, as shown, and then they gently lower the block. So I'm not going to assume energy is conserved here because somebody like took this, was holding it, and then gently lowered it. Which of the following, so the outside force, right, work being none, which of the following describes the change in energy of the whole system? So think about it, your gravitational potential energy obviously just changed. So gravitational potential energy is mgh, mass of 1, g. Your height, right, the height that it just changed by was 5 centimeters, which is divide by 100, 0.05. So then that gives me just 0.5. That's my change in potential, gravitational potential. I just lowered this, so that is a loss. It's a negative 0.5. Now, you have a spring here. It was uncompressed, and now it's stretched out, so I just gained spring potential. So the change in the spring is 1/2 kx squared, which is 1/2 k is 200. X is 0.505 squared, so that gives me a change of 0.25. And because it went from not stretched to stretched, I just put more energy into it, so it gained energy. So if you lose 0.5 and you gain 0.25, you still lost a 0.25, so then B. Two objects, A and B, they both start from rest. Horizontal surface, which means that you're changing kinetic energy with the applied force because it's a horizontal surface, it's not increasing potential up or down. Which object will be moving fastest at x1? So think about the one that's moving fastest is the one that gains the most kinetic energy. Gains most kinetic energy. The one that gains the most kinetic energy is the one that has the most work done. Work is just the area, so then you don't have to calculate it, right? Area underneath. A has a greater area, so more energy is going into it, so it'll be faster at the end. So this guy. Level track, we've got a force parallel to the axis. As it goes from 0 to 7 right here, what's the net change in kinetic energy? So this is just change in energy, which is just the work, which is the area. So that's 12 here. That's 3 times -3, which is -9. 12 plus -9 is just a positive 3, so it's still an increase because it's ending up positive increase of 3. A box of mass M is lifted from a height h naught, so let's say it's going from h naught to h1. Find the work done, so work is just change in energy. The final energy, right, would be mgh1 minus the initial, which is mgh naught. You also can think about it as mgh1 minus h naught, right? It's mg, the change in height, is the work done. Here, now it's lowered from here to here, from h1 to h naught. So still work is change in energy, except for now it started with mgh1, and now I'm going back down to mgh naught, so this is the change now. Oh no, I did this again. Final minus initial, final minus initial. Oopsies. Because these should be the same but opposite. So this one would be positive work because h1 is bigger than h naught. This one would be negative work because you're doing this minus this. So it makes sense. Here I'm increasing the energy, here I'm decreasing the energy. And overall, the work done from start to finish, right? If I do this much positive work and I do the exact same amount of negative work, then this is going to cancel out. So that would be a work of 0. You also can think about it from here to here. I'm back at the same position, so then the energy has not changed.